Hello, my name is Tong. I'm a PhD student in University of Luxembourg. Today I'm going to present our work characterizing the impact of network delay on Bitcoin mining. This is a joint work with Professor Jérémie Decouchant, Professor Jiangshan, and Professor Paulo Esteves-Verissimo. The Bitcoin market capitalization has increased rapidly in the past decade, as we know. The main innovation of Bitcoin is actually the Nakamoto consensus, which was the first to solve the Byzantine generals problem in the asynchronous and permissionless network environment. What is Nakamoto consensus? It is actually a set of many rules, which includes, for example, proof of work, the longest chain principle, and incentive mechanism. In this system, users generate transactions, miners verify the transaction, and are incentivized to solve the crypto puzzle. As long as a block is discovered, it would be relayed in the P2P network. When the other miners receive the block and they haven't found it, they will adopt it and work on it to find the next block. Previous work has shown eventually only the longest proof work chain will be maintained by all miners, which means the weak consistency would be achieved. And the importance of network delay has been mentioned in the previous works. A simple observation here is when the miner has a relatively small network delay, it would help the miner to work on finding the next block earlier than others. And the miner would have a higher chance to win the conflict when the concurrent blocks are discovered. The open question here is, can we quantify the block reception latency between miners? And what are impacts exactly? To answer this question, first we need to find a way to be able to measure the block reception latency between miners, and we need to quantify the impact and evaluate if they have an impact on miners' revenue. The common way to measure the cryptocurrency P2P network is to deploy monitoring nodes in the network and establish the connection with the reachable nodes in the network. Then for each block or transaction message, the observer would receive it k times, assuming there are k reachable nodes in the network. Based on the message arrival time, the block propagation delay or transaction propagation delay can be estimated. However, except for the reachable nodes, there are many unreachable nodes in the network, which are either fully connected or they do not accept any incoming connection. Therefore, this approach has some limitation. For example, you need to have many monitoring nodes in different locations of the network in order to get a good network coverage. Moreover, the locations of miners cannot be identified. It is difficult to use this approach to infer the consensus delay between miners. In this work, we designed a novel tool, miner entanglement, to measure the consensus delay between miners. The idea is to leverage mining pool API. We register our machine as a subminer in different mining pools and to connect with mining pools. And then we can directly receive the block information from the mining pools. And by doing so, our measurement does not suffer the uncertain delay from the P2P network, and the block reception latency between miners can be measured accurately, except for some anonymous miners that we cannot connect with them. In our experiment, we connected to 70% of Bitcoin hash power, and we report the consensus delay between them. The second challenge is to quantify the impact. In other words, we want to know what exactly the advantage or disadvantage that the miner can have because of the network delay. As you can see in this diagram, we have 5 miners, M1, 2, 3, 4, 5, and B0, 1, 2 represent the blocks. BO is discovered by M2. Apparently, M3 received BO earlier than M5. So this time difference is the advantage for M3 and the disadvantage for M5. The question here is still, how can we quantify this impact? In this work, we define 3 metrics to quantify the impact of network delay. First, we define effectiveness ratio to capture the useful computing time in the mining process. The block reception latency is actually the useless time. Miners waste their computing power between the time when the next block is already discovered and the time when they receive it. We then use EHR to represent the effective hash rate. Because of the network delay, miner's effective hash rate is actually smaller than the real hash rate. Lastly, we define EHR share to quantify the impact of network delay on block revenue. In the mining race, your advantage is others' disadvantage, and others' disadvantage is your advantage. Therefore, the probability of finding the next block should be represented by EHR share, which is calculated by using miner's effective hash rate divided by the global effective hash rate. In this work, we deploy a machine to use miner entanglement to connect with 10 Bitcoin mining pools, which allow us to measure the block interval, block reception latency between mining pools, and effectiveness ratio. We also deploy a Bitcoin full node in the network to compare with mining pools. As a result, the block intervals approximately follow an exponential distribution during a week. Recall that our metric not only depends on the block reception latency, but also the block interval. Assuming that a pool has a few seconds network advantage, when the block interval is small, for example, 10 seconds, 50 seconds, it would have a significant impact. So we say a few seconds delay is important. This figure indicates the effectiveness ratio distribution of 10 mining pools as well as a Bitcoin full node we deployed in our experiment and a pool used miner entanglement to improve their connectivity. As you can see, the purple line represents the Bitcoin full node and gray line in the right of the figure represent the pool used miner entanglement. It is obvious that different pools have different mining efficiency due to the network delay. It is not a surprise to see that the Bitcoin full node had the worst performance. The average effectiveness ratio during a week of the Bitcoin full node was 0.952. Remarkably, some mining pool had a similar performance like the Bitcoin full node, which implicate that some pools might just deploy a single Bitcoin full node in network to exchange message with others, which is absolutely not good. And some big pools had a better performance, as you can see. They might use some method, for example, the fast relay network or Falcon network or other method to improve their connectivity. The pool used miner entanglement had the best performance, which was 0.997, close to 1. This shows the advantage that if the mining pool use miner entanglement to improve their connectivity to receive the blocks. By using manner entanglement, we report that the consensus delay between 10 mining pools was from 0 to 13.76 seconds in average during a week. Some pools received the block earlier than others, some pools received the block later than others, which demonstrates that the disadvantage or advantage of different mining pools. So this impact actually was more significant in the blocks that have small generation time, as you can see in this figure. When the block interval is smaller than 200 seconds, the disadvantage of the worst connected pool is increased. To validate this impact, we calculate the actual revenue share of mining pools during a week based on the on-chain data. The result proves that indeed, when the block interval decreases, the advantage of the worst connected pool is increased, which means the worst connected pool would lose more blocks. To further evaluate this impact, we use the Monte Carlo method to simulate 10K blocks. In this simulation, we assume the anonymous hash powers connectivity in 3 cases. Either they were fully connected like a Bitcoin full node, or they have a good connectivity like some big mining pool, or they used manner entanglement. Based on that, we show a good network connectivity would give more block revenue to the pools. For instance, when the anonymous hash power had a bad connectivity, as you can see the blue line in this figure, pooling was able to earn approximately 137 Bitcoin in addition per week, which is a lot. So this shows the impact of connectivity power. The implication here is if the big pools are always more profitable than small pools or small miner, then the owners of the computing power would leave the small pools and join the big pools, which would lead to the centralization issue. Our next interest is what would happen if all miners realize this and try to improve their connectivity. We built the game theoretical model based on the literature, where each node can select their neighbors, and they might have different strategies to maintain their connection. And they want to use the lowest cost to have the smallest delay. In this game, the network consists of n nodes, and where we have k mining nodes, and each node can maintain L connections. We prove that if L is greater than K, a complete graph would be achieved by using manner entanglement, which allows a Nash equilibrium to reach. And when L is smaller than K, which means when the node's connectivity cannot support them to build a complete graph, what would happen? To answer this question, we use a well-established simulator to analyze this phenomenon. We modified this simulator. In process, we create an interface in the simulator, which allows us to observe a dynamic network and to see the network evolution when the node use different strategies to select their neighbors. Here we mainly focus on 2 scenarios. First, the default scenario, where each miner selects its neighbors randomly according to the default protocol. And second, all selfish setting, where all miners, they are rational, they want to maintain a connection with powerful neighbor. As a result, we show when all miners are rational, they would only connect with other miners that have the similar hash power, like the network associativity theory. Therefore, the top miner can increase their revenue and the small miners have to suffer a loss. So the game would be the game of the rich get richer. Here are takeaways to answer the question we had at the beginning. In this work, we designed a novel tool, miner entanglement, to measure the block reception latency. And we define new metrics to quantify this impact. And we emphasize miners' revenue not only depends on its computing power, but also the connectivity power. And we say a few seconds delay is important in Bitcoin's mining process. Considering there are many Bitcoin-like cryptocurrency, some of them reduce the block interval. For example, in Ethereum, in the current version of Ethereum, later on it might be POS cryptocurrency, but now in the current version of Ethereum, the block interval is from 15 seconds to 20 seconds. So it would be interesting to use our tool and metrics to evaluate other Bitcoin-like cryptocurrencies. So I'm going to end my presentation here, and thank you for your attention. If you have any question, you're welcome to drop any question my email address. Thank you.